Yeah, ladies and gentlemen, it's a great pleasure for me to welcome you as the Wednesday afternoon last week, the week before last week, since we started with our webinar to our weekly webinar about hydrogen and hydrogen derivatives, possibilities and constraints on behalf of the various organizers, which are on one hand side the University in Patna, which is the Green Hydrogen Association Tunisia, which is the German Engineering Association, as well as Hamburg University of Technology. So warm welcome to everybody, and it's a great pleasure to have you here again in this lovely Wednesday afternoon on Valentine's Day. So therefore, this is the love what we have according to hydrogen. With this, thank you very much for being here, and I'm be sure that we have a very exciting, a very interesting program this night. After last week, where we discussed a little bit hydrogen methanation aspects, so we learned about thermochemical methanation, about the basics from Selina from the German Biomass Research Center. Then we learned something about the biological methanation, about innovative approaches, what we can do with biology, from Johannes Gescher from Hamburg University of Technology. And we learned that there are a lot of hydrogen projects ongoing on the one hand side, on the thermochemical side, as well as on the biological side, from Tilman Schildhauer, from Paul Scherer Institute in Switzerland. So therefore, yeah, we know now that we can convert hydrogen easily and relatively efficient to methane. And then the question is, if we talk about global energy systems, how we can transport this methane from somewhere, maybe in North Africa, or maybe in South America, or maybe even in Australia, to transport this maybe to Germany or to Europe. And therefore, we have already quite some experience because, as you might know, we import already quite a lot of methane up to Germany or to Europe, which is mainly transported by pipeline in the old days. And in the younger past, we transport this as liquefied natural gas, but still this is from fossil fuel energy. But nevertheless, we are able also to transport with the same technology, with the same approaches, we are able to transport also green methane. And therefore, it's my great pleasure to have two presentations about liquefied natural gas or liquefied biomethane. One from Hans Großmann from GOC Engineering in Bonn. He will give us a presentation about LNG, methane liquefaction and regasification processes based more on the technology side. And afterwards, Professor Sören Ehlers from Hamburg University of Technology and from DLR, from the Institute for Maritime Energy Systems. He will give us a presentation about large-scale transportation of LNG materials and concepts. So from that point of view, we continue where we have stopped last week. And now it's my great pleasure to ask Hans Großmann to give us his presentation about the possibilities of LNG liquefaction and regasification processes. So, Mr. Großmann, Hans, the floor is yours, and we are waiting for your presentation. So it looks like as if there is some technical problem with him, because 2 minutes ago he still was here.
Yes, but I'm still there. Can you see me?
We can hear you. We can see you now.
Yes, okay. Perfect on it. And I will share now the presentation.
Yes, please.
Oh, where we are? Here. Here we are. And here we are.
Okay, it looks like as if it works. So thank you very much for being here, Hans. It's a great pleasure to have you here, and the floor is yours. And now you can tell us about hydrogen and hydrogen derivatives and LNG methane liquefaction and regasification processes. The floor is yours. Thank you.
Okay, thank you, Martin, on it. Good afternoon or good evening, ladies and gentlemen, on it. Yeah, I'd like to give you some overview on it, how it looks like when you start to liquefy methane, or if, on the other side on it, if you then later on will still be regasificated in the part on it. Let me see on, we will have some introduction, some general fundamentals. Of course, we have to see where we are in. Then we start with the natural gas liquefaction. I call it natural gas liquefaction because what we are doing is not liquefying normally pure methane. We are normally liquefying natural gas. It will come then with transportation storage, just a brief, and then we go into the final part on it of the regasification. Give me some time to just say on it where we are in our where we are coming from GOC. We are an engineering consulting company in this field of loading and storage of liquefied hydrocarbon. It starts from even from propane, butane, propylene to ethylene, but up to also LNG. And there we are offering various services in this field. Where we have been in various energy projects all over the world, starting from import-export facilities in Norway, but up to FSRU in Italy and some others also. Actually, we are also working on the import facility, which should be developed or which should be built in support of Wunsbüttel. Where we look into the overall view on it, we are first starting on this, where all this process starts within the liquefaction plants, somewhere where we have good sources of natural gas and to import there on it, but could be also where we have good sources of biogas on it. So it's various. So we have to see where we are in on it. Then we step over on the other side to see where we have then the import or where we have to export our product, our LNG, and what we do on it to vaporize it then and to go to our final clients. Some small footprints also here to saying what we are in. What is LNG? Once again, LNG is not pure, it's a mixture. LNG mainly is of course methane. It depends on it from what sources you are getting it. We have put in there on the right hand side a typical composition when you are saying I like to have LNG on it from one of the key market players, which is some Qatar, and you see there's a right portion of methane, but still others in heavier hydrocarbons like ethane, propane, or others. And this could vary all over the world, depends on it from what sources you are getting it. Therefore, there's always a range on it, and always we have to look into. LNG is odorless, colorless on it, is not reacting, is normally stable on it, not toxic, not corrosive. So it's you have to, if you have to keep it under liquid condition, you have to put it in isolated cryogenic storage tanks. Some things on the boiling points on it, somewhere around minus 160 degree at our atmospheric pressure conditions on it, at 18 bars, somewhere around 110. So it's not pure on it. The density even varies as well also on it. So then the range on it between 430 kg per cubic meter to 470. Always this, once again, there's only some figures on the typical figures on it. It could always vary. This will be then part of your design criteria. Liquefaction. What is behind the theory of LNG liquefaction? In the case on it, what you like to do is normally you want to be as close to the natural cooling curve of natural gas, which has normally three main sections on it, where you're having some type of pre-cooling on it. You have your liquefaction zone somewhere in the middle, and you have some type of subcooling on it. We come later to the point what this means with mixed refrigerant and the others on it, but just to show on it, that is the idea behind on it. You normally use say various combinations, series of expansion compressing cycles to take out the heat on it with heat exchangers, all different types. It's all bits and pieces you have to put together that you're coming as close as possible to the natural gas cooling curve to run on it. This is the main part all behind. When you see now the different type of processes are in on it, they all into saying can we come close as much as possible to this curve. In general, there are three main different types of cascade liquefaction processes. One is a cascade, one is this mixed refrigerant, and the other is also some expansion process on it. So if you divide this somewhere in the area, there are the main groups on it. Of course, on it between, say, within cascade liquefaction process, you can also have some mix or pure refrigerant. We will come to this in a minute. Starting with the easiest type of liquefaction on it, if you have pressure enough in your system, it means high pressure pipeline system, whatever it is on it, you can take it, you can use it like an open cycle process on it. That you just if you compress it to a high to a high pressure on it, starting then to liquefy it, or started then to have in Joule Thomson use this for the cooling back on it. And at the end, if your pressure is high enough, say around this figure of 100 bar, 200 bars, and so on, with your Joule Thomson expansion, you will getting then out an output out of this as a fraction of LNG. It's not too much not too much efficient, but we have seen already some projects, mainly in Eastern Germany or Eastern Europe or in Russia on it, where they having high pressure on it, where they use it. Or if you have if you're somewhere at the end of an pipeline grid on it, where you have some of this pressure, it works on it. But once again, it's not very effective and efficient. We will come this also to this later on. One main thing is to say, because we are starting with all this process on it, you have already to look into your gas treatment. When you're taking out gas, natural gas out of the earth or taking out over the pipeline, it is not suitable to liquefy it, because there are still components in CO2 and others on it which you have to take out. Therefore, if you look for a footprint of an energy liquefaction plant, you see always at the beginning a huge equipment with only the function on it to treat the natural gas first on it, that you are able on it to introduce it in your liquefaction plant. There's always is one thing on it which is not part of this session here, but you have always have in mind on it that there's a huge amount also a huge investment, huge equipment already needed also to treat your feed gas. Here we have a single nitrogen expanding process on it. This works just by compressing and single work expansion of nitrogen. The advantage here, the nitrogen here is practically it remains in the gaseous phase. And only you need your sensible heat, which you take out on it for the cooling. On the other side there, you need a huge amount of nitrogen, and it's not so very efficient on it. Which means on it, we come in here with the nitrogen on it, have your heat exchangers going out, and there you have the various loops you can have to cool then some of the natural gas with the booster expander and so on. There are flexibilities also that you're adding a second work expander cycle on it. So this is just to show you only this is so-called the nitrogen expander process, which is also in the market. How the market works on it, we will come also later to this point. Or we're coming to this point on it. The majority of liquefaction processes in the world, and here's around 68-70% of all the large-scale plants are working with this type of dual mixed refrigerant process, patented by Air Products and Chemical on it, and have a long lead experience, and this is so-called the C3 mixed refrigerant process. It's just using process, say somewhere using propane as a type of pre-cooling already to take out already some heat on it, and going in a central cold box heat exchangers where you have a closed loop of a mixed refrigerant on it, and then you're going back with your the natural gas on it, and it's a natural gas out of at the top, and then in counter to your mixed refrigerant some product, you cool your liquefy or subcool somewhere your natural gas. The mixed refrigerant here is it could be a mixing of nitrogen, methane, ethane, and propane, and all where are they arriving and to start to liquefying on it or vaporizing on it. There you have your individual sections in your cold box. This comes on it that you have subcooling that's from up to minus 150 degrees, and then you're going out to your storage facility and maybe make your final Joule Thomson when you're flashing into your tank. This is a dual mix refrigerant. One of the most known process in the world, a couple of already decades, and of course works also properly on it. There is some extension or some others that's called this expander process, where you're using natural gas and nitrogen as an refrigerant on it. There are two independent cycles. There's one cycle using nitrogen as normally methane as cooling fluid, and the others there is also nitrogen as a closed cycle, and this provides you cooling at the moderate temperatures. And the nitrogen, then some of the other sides, and then some of the nitrogen cycle gives you then the lowest temperature where you can cool down, or can you then liquefy your feed gas. There are some options on it that you can where you take out your heavy hydrocarbons. So that are most of the things are things where this process developer are having their expertise. Both cooling cycles, nitrogen as well as also some methane, are remaining in the gaseous phase. And that means there are no too much problems in designing other things on with respect to two-phase flows in your system or in your cold box. Dual fuel expander process. Besides this dual fuel and the others on it, one of the major processes which is in and which is right from the beginning and simple on it is a so-called refrigerant cascade process or pure refrigerant cascade process. What does it mean on it? You have independent several type of refrigerant cycles on it, where you can play on it to say liquid to gas, gas to liquid. It means you can really have your normal refrigeration cycle. That is based on really that you have pure 3, 4, or 5 pure cycles on it, and principle is that principle from Joule Thomson expansion in the cycle around on it. Most of the refrigerant using in the market are that we're having propane, that we're having ethylene, and methane in it. You can have all type of cascades. You can make your cascade up to whatever you want on it. However, most efficient is as a selection from this market on it to having only three main fluids on it, working independent on say on the heat exchangers, and then say liquefying, subcool liquefying, then also the natural gas, the LNG. So that is a typical just cascade process, well known also in the market, used mainly for smaller plants on it, but all components are standard components. The main work here is only to look into where you optimize your process borders. The other one is then compared to what we have seen with this pure cascade process on it, there is a single mix refrigerant process, also well known in the market on it. But there it runs the process on it. There you use refrigerant made normally a mixture of methane, ethane, butane, or nitrogen. This could be then in one cold box. You see that there are different zones on it or different heat exchanger, but they can also be in one single main heat exchanger, or say so-called cold box. With this single mix refrigerant, you can really come close that you can enable your temperature profile very close as possible. It means you can optimize your cooling curve or your expected cooling curves on it. That means you closer to your temperature profiles on it, where you're in on it, you can then have the advantage of a reduced compressor power and in higher efficiency. And whether you can have double phases, you have this double phases, and that you are on one side you are having to go in from liquid to condense, liquid to gas, on vaporizing, on the other side to condensing also in some parts. That's all is part of the main heat exchangers they're in. And once again, they are also, we have different pressure, say levels where you're working on, which means also you can optimize also their some of the efficiency. That is a single mix refrigerant. Once again, also well known in the area. Just to have a small picture on it, how it looks like with the things on it. This is a typical cold box prepared by the big makers from Linde or Air Product or the others. And you can see here the cold vaulted on how many small tubes are, how many different types of connections are in warm side, cold side, intermediate side, and all in this tubes on it there is working on it there. Sometimes it's condensing and some parts is evaporating. So that is one of the core design challenges on it to optimize this type of liquefaction, even to know what is happening inside the tubes and in what area is sometimes happening on it. You can imagine that you cannot have in all bits and pieces temperature sensors or on it to look into on it. So that is one of the core challenges in designing or in even in the process simulation of this type of equipment. So once again, we have the three different types on it. Could be double on it. We normally say cascade, mixed refrigerant, and expansion processes. Having said this on it, you see the complexity of this type of liquefaction plants on it. There you can see that some of the design options where you have to start on or where you have to look into is somebody starting to designing this type of process is always a mixing, compromise, optimization of power consumption, of energy consumption. Even when you look into on it, when you only look to power consumption of your compressor and so on, that is not enough on it. You have always to see the total system here on it. What is also some with your shaft power, with your efficiency of the heat exchangers and of the thing itself. Beside, of course, capital costs, all the commercial things on it, and even operating on it. If you have some type of batch operating, if you have continuously, if you're having a variation of your operation or you're running on one line, and how much you like to generate and things on it. And this combined also you have to look into where you have maybe no chance to changes, which is your maybe natural gas feed conditions on it. Also there to optimize what is the best or what composition you have to achieve and where is the best arrive on it with respect to temperature, pressure, and flow. The inlet also temperatures with the minimum internal the meter of the heat exchangers is one of the figures as well also. And once again, efficiencies of compressors or expanders besides the LNG rate. So that's when you see the different type of processes, you see how difficult or how challenging is it on it to arrive at the end saying my plant is the best one or my liquefaction is the best one on it. You hear it always in the market on it, but once again, to arrive there is not so easy. Therefore, I'm assuming people will ask on it, yeah, what is then now for this processes the best, maybe the best train efficiency, for example, or specific powers. You find in the market, you find in the public on it some specific figures which I have put in here on the table on it, where you can see on it that some specific power on it to produce how many kilowatts you need to produce 1 ton per day of LNG and so on. There you see the different things on it, which of course varies somewhere between 12 kilowatts on it up to 15, 16 kilowatts. Once again, there's figures on it. Nobody will give you in detail all the information on it, but that's what's coming out of the common community on it. However, this is one point when you look to the power. The other thing is looking to this, say, to the train efficiency of the entire process. And there's also when you look to the gascade or somewhere of the in the dual mixed refrigerant or semi or the C3, which was the main used some liquefaction process on it, the seat array on it, you see there's there's less power in it, but it's not even with a good or with the highest efficiency as well. So therefore, this is normally commonly in the area on it. However, they are sometimes limited in the train capacities. If you can go further up to 5 or 6, say, BCM per year or a million ton per annum. So therefore, it could be if you need really more, so on, then you have to install say more than one train. This goes then in the cost. Looking to the part of biogas liquefaction on it. In biogas liquefaction on it, which is small liquefaction, there's normally there you can use normally simple gascade processes, which can be used on, or sometimes also just cooled against nitrogen. That is aber more when you really look to the small scale liquefaction. This is really small scale liquefaction, and there even you cannot use the large patented say processes on it. There you have to come back on it and saying what it could be the best as a compromise of a small gascade on it, or do it with liquid nitrogen. This is some overall picture about on it where we are on this liquefaction with this maybe summary on it to see where are you in with specific power requirements or with train efficiency. Going now on the other side on it, so we have produced our nice LNG, have good market, and now we have to sell it. We go now on the other side by having starting that we have a receiving terminal on it. That is just to have to receive LNG carriers, stored in tanks, vaporize it or regasification again, and go into your natural gas grid or into your truck loading, wherever it is on it. There are some parts also that we have to design this to look into that you can cater your client requirements at all areas. Around weather conditions. So that is all in where you're saying, okay, my import terminal is then large enough. Transportation, I guess the seaside will come later on with the second paper. On the right hand side, you see a typical full containment storage tank for this LNG, having an inner tank to store the liquid as an open cup, have an insulating between at the bottom and at the top and on the side, and have normally in Germany, due to safety or in Europe safety considerations, in full containment outer concrete side, and the roof even also somewhere from concrete. Typical insulation going up now to 200,000 cubic meter per single tank or 240,000 per single tank. So the largest so far in the 220,000. Regas, we've shown about, so what we do there on it, we come from the ship, stored in the tank, very simple on it, having type also an say on boil-off handling system on it to maintain the low pressure, the low temperature in the tank on it by a recondenser, take out the LNG on it, go out on it, and have a type of system to vaporize it. Normally, you need a high pressure pump somewhere in advance on it due to your pipeline pressure. In addition, you can also take out and go by rail, by truck, wherever you want. The principle is what you like to regasificate on it. It's just simple to bring it back into gaseous phase on it and have a slightly temperature above 0 degree on it to maintain this temperature in your pipeline system. And there is always there are a lot of potentials where you can really optimize some of the economics of the process. And cold turbulation is one of the main principles before you starting anything on it to look into all this regasification. Go to your neighbors, look around and see, do they have any type of waste heat, of warm water from power plants, from whatever you need on it in sufficient maybe composition and some capacity, which you can then use on it to vaporize it. That is the best way on it to optimize your entire system, to look in the area and not to build in expensive it's an independent vaporizing concepts on it. So please look into your neighborhood and ask them for waste. Ask them just simple for waste heat. There are different types of vaporizers. There are mainly, you can say, there are open rack vaporizers, submerged, and others are intermediate fluid and heat transfer fluids and direct and also ambient. We are coming to some of the common parts now on it. One of the main use in base plants are open rack vaporizers. Open rack vaporizer is just simple on it. You're coming in with your LNG somewhere, and against your LNG, you have a free flow of water, of heavy water on a continent, and to this, and your LNG are in pipes, and to this water on it, you vaporize then the LNG, and it goes up then in the upper part. It could be somewhere seawater, it could be also warm water from your nearby power plant or wherever it is on it. You see it also on it. It comes in here from the bottom, goes out, and then goes out on it, and the water goes back then somewhere in a retention or in a trench. Common practice, most of the say a lot of import terminals having this type of open rack vaporizers. Even there, where you have, for example, in regions where we have warmer temperatures on it, and where it could work on it. In our region, or in regions somewhere where you have minus temperatures on it, then there's only the chance to use this type on it if you warm up your feed stream of water or have warm water on it. But commonly they are more practiced in warmer regions. So it looks like they are very heavy, they are loud, noisy, and so on it. And you can already imagine on it that there are a lot of turbulences, somewhere in, a lot of water in which are going on it. Still, there's some icing in and so on. And on the other side, you have to avoid that you have to see that you have always a water flow, not to having some tube ruptures or some icing completely around your tubes. So normally they are easy operating, low operation costs. Most are then say static some equipment, no pumps or something else needed. Simple construction, stability of the heat transfer because you have this free falling water film therein. Alternative, once again, you have a warm loop on it, a bypass loop on it, where you can use them also over areas. There are more for large facilities. Due to the reason on it that you can during wintertime not use this, the open rack vaporizers, there you have the type of the so-called submerged combustion vaporizers. Submerged combustion vaporizers is a big pot on it where you have water in, and you heat this water with a flame on it, with flames on it, which is somewhere inside your systems, which means you have a type of a burner system with pilot burner, central burner, main burner, where you need fuel on it. You have your water tank, and this fuel, this flame or the flames on it warm up somewhere this warm water. There's a lot of turbulences then in on it, and via tube system or bundle system on it, your LNG comes in on it and will be then vaporized against this water. Okay, you have, and then somewhere we have a vent stack on it, and that's the system how it looks like on it. One of the main advantage of this one is on it you need really a lot of it's a fuel gas which goes up to 1.7% of your total say some throughput of gas of what you are producing on it. And you can imagine on it that is already expensive on it to run this type of submerged vaporizer. Normally used only in peak during wintertime or where they need them, or used as in backup if your key vaporizer system is not in operation or due to maintenance or other reasons and so on. Then this is terminally used as a backup. You can find them also in smaller say configurations for use in Germany, also in some peak shaving plants. So they are available also in various ranges. that's a little bit how it looks like internally. This is a bundle which is internal in, where it goes in, and later on your natural gas goes out. On it, the in is somewhere from the bottom side, out is from the top side, and here are six SCVs on it. You see this basin on it where the heater is in, warming up, and then the vent stacks you need to depend your emission permit summer requirements according to TH Luft. Or here in Europe, according to TH Luft. On it is somewhere common practice. You find them still in the US in some parts on it. In some other areas, submerged combustion vaporizers. Developed in some areas where you say you like to have a close and a safe system to avoid any freezing, for example, on it. This was a development of an intermediate fluid condenser, fluid vaporizer on it, which has an intermediate refrigerant, for example, propane, and this acting that you are then you're having an indirect vaporization. That means you have not a direct link to your seawater or to your water, to LNG, to avoid any freezing problems or tube ruptures and anything on it. LNG goes in here on it, will be then also vaporized against condensed propane and goes back on it. There's a second part on it where we will a little bit heat it up, and then it goes out to your natural gas grid. On the other side, you're getting seawater or hot water, wherever it is on it in your system. On the tube side, will then condense, will then vaporize the propane in a closed cycle, which is in here. And then once again, this will be condensed then against vaporized, let's say, LNG. Well-known practice, works perfect on it. How they look like on it, they are normally used or they're normally installed in a horizontal area on it with all the stuffs around. Well-known. You can also use instead of propane some others, so that is somewhere practical. In respective heat source, if you have seawater in the others on it, always heat integration. If you have some other fluids on it, easy to control, to operate, very low freezing risk. Is always a point if you're doing your hazard or your safety studies. In on it is only a limited amount of propane as a closed cycle in, but once again you have not the problem of freezing, and to do on it low maintenance costs, and more or less no emissions with respect to if you're not burning something. And another way to do it also, there are of course also direct fluid vaporizers in the market. They're just simple shell and tube vaporizers where you directly vaporize against water or seawater or fresh water against or something else, or some of the LNG. Also there, it's unexpected to do. But once again, you just go in on one side on it, only on the tube side you are in, and on the other side you have your seawater or your heating source as water on it, and this against on it will be then vaporized, and on the other side you will take out this natural gas. However, there's always some safety concerns on it if something not working on it. For example, if your seawater entrance is blocked and you're getting not sufficient seawater, then you have to, then there are some safety concerns regarding freezing, relieving, tube rupture, release of LNG. But once again, also they are in the market on it. It looks more or less similar to the IFVs on it. Some are horizontal on the ship, for example, for FSAUs, and then also vertical situations. One further group which you maybe have seen already on it, are ambient air vaporizers. These are, for example, also parts you can use in smaller capacities like biogas and the others. What is this? Maybe know it from liquid nitrogen on it. There are let's say aluminum or fin tubes on it, place on it, which will be then vaporized against the air, or will be not vaporized against the air on it. You will use the free air on it as a heat source on it to vaporize then the product. You have normally 3 sections. For example, one is maybe in operation already, one is standby, and the other is maybe the other is already, because if you have too much icing around on it, then you have to stop, and then you have to warm it up again, that your ice ice area will be then warm up. Works. It's easy operating, nothing too much to do on it. Just open the wells and so on, and maybe controlling your icing on it. However, in our region on it, what you see always when you have an LNG and so on, you see normally not, you see mostly on it condensed air, condensed humidity in the air. That means if you have a large installation of this ones, this could be that you have to getting type of a so-called fog bank, means heavy fog. That could be then maybe disturb your traffic or something, your nearby neighbors, whatever it is, and so on. So that is one of the disadvantages. The other one is easy operation, easy cost. Vaporizer. Yes, this brings me already to the end on it, which normally is in then the innovation of the day. When you look here to on it, that is an example how you can do also environmental friendly block of a valve. That is really a picture made on it in an LNG installation a couple of years ago, which was somewhere blocked in, not in operation anymore. And after a couple of years on it, you can see it on it that the first 3 starting on it to take back their plot. This brings me to the end of of my presentation. Thank you, and the floor is open for questions.
Yeah, Hans, thank you very much for this very nice and very interesting presentation. So we really learned quite a lot how we can bring, let's say, LNG or synthetic natural gas into the liquid phase and regasify it at a point of destination. So thank you very much for that. I was really impressed about these very nice photos, what you showed about these different units. So they are really huge. So thank you very much for that. We will come back with a small roundtable discussion after we finalize then, or we finish with the next presentation. And now it's my great pleasure to introduce Søren Ehlers. He is the head of the Institute for Maritime Energy Systems, and he will give us an update about the large-scale transportation of LNG materials and concepts. So, Søren, the floor is yours, and we are very much interested in your outline. Please go ahead. Thank you very much.
Thank you very much, Martin. My pleasure to be here, and I will jump right into the slides. Now, we have seen what we need on the shore side on each end, whether we will regasify or liquefy the LNG. And here what you can see is basically where around the globe we are transporting the LNG. And as usually, the demand is not at the same location as the production takes place. So this is why we need to have some logistic systems in place. And essentially, we have North America, from which LNG is exported, some parts in Africa, some parts here in the Middle East, and a lot of export from Australia up to the north from there. And analogously to the presentation we just saw, you will obviously find these liquefaction terminals and regasification terminals at the corresponding locations on the shoreline, so that when you want to export, you will usually do this in a liquid form, because then you have the LNG that will allow you to have a higher energy density given for the volume that you want to transport. And that's the whole point of why we do that. And then it's a bit impractical at the destination site to further utilize liquid natural gas at that cryogenic temperatures. So we use that in the gaseous form. And a few numbers are here just to show what is the global trade. In 2022, we had about 400 million tons That's a 7% increase compared to 2021 that was traded globally. And there's mostly or mainly 20 importing countries, mainly the EU and East Asia. And we have about 46 exporting countries. And well, because of certain political conditions we have in the world, there has been quite an uptake in imports on the EU side. And if you look how many ports worldwide with LNG bunker facilities we have in 2023, you see that a lot of them are in Europe. We have them in the US and we have them here in the Far East. And then there's about 50 further facilities planned by 2025 to be in operation. And on the European side, maybe the fairly interesting point here is that the EU imported about 1/3 of the global LNG deliveries in 2022. So the biggest importers here would be Spain, France, Italy, the Netherlands, and Belgium. And by looking at that map, you get some understanding of obviously that these import terminals are at the seaside, and where we have some in operation already, where we have expansions planned. This is the ones that are half orange. We have very few that are under construction, one in Finland, and then we have several that are planned and partially are already in operation, obviously. And you see a few pipeline projects that are also ongoing, because it doesn't help us if we only have the LNG at the port. We usually need to transport it further to the hinterland from that location onwards, and maybe on shorter distances through the Baltic Sea and to some other parts. And very few gas storage projects that are currently ongoing. Now, the total LNG capacity in 2022 was about 487 million tons. And it's expected to increase even further by another 12% all the way to 2027. And there will be more countries that will get into the LNG production. So it's still a very strong market, with the key LNG producing countries being the US, Australia, Qatar, Malaysia, and Russia. And there is also quite some growth rate to be expected in these specific regions, with the different colors, green being the highest, with more installations that are going to take place. Now, when we look at the price, I just found that quite interesting to see that, yeah, there are some fluctuations for certain reasons that we had in the past, unfortunately. But you can notice that the LNG price actually became lower and lower. And if you compare that to the oil price, which is also roughly at a constant level around these $80 per barrel, then you can see that it is a quite viable option in comparison to oil. And since this ended about a year ago, what I just showed here in the graph, I just picked up some numbers last night. So the chart that you just saw went up to here, then there was some increase, but we are basically back at the same level for the LNG. So the price seems to be comparatively low and possibly rather stable. Same stability we have for the oil, but on a much higher price level. So that makes it still for a nice product to be shipped around. And that brings us to the part on how we are actually transporting the LNG. And ideally, we do that on the water, and we use tankers for that, because we saw that some country on one part in the world produces it, and another country further away that is connected by sea wants to import it. So the world fleet for this is about 734 LNG tankers that we had by the end of 2022. And they have a capacity of 2,500 cubic meters to almost 300,000 nearly, if you think of some large offshore storage units, but about 260,000 cubic meters for the tankers, which makes for a transport capacity of a bit more than 100 million cubic meters that we have on a given time. And the scales are large, the energy demands are large, and one reason we need to liquefy also is this is the only format in which we can transport the natural gas so that it is efficient when it comes to how much energy we actually transport, given the density. And there's essentially two ways or two ship types that exist for this. The left one you see here on the bottom would be an LNG tanker with a membrane tank. So it's not protruding much above the deck, and it kind of follows the line of the vessel. Or we have these spherical tanks, mostly built by Moss Maritime, that nicely use physics, because obviously on a sphere you have the lowest area to contain any given amount of volume. So if you think of insulation properties, then this is quite smart. But on the other hand side, it doesn't really fit the ship shape, because the ship is more like a long shoebox. And if you put spheres there, you lose a lot of volume and you increase your center of gravity quite a bit. And the other thing is, as you can see on the right top, you need a lot of building capacity and actually a mold to build these spheres. And if you want to change the size of the ship, for example, if you make it longer, you could just make it longer by one sphere. But if you make it wider, you need a new shape for the sphere to be able to build that. And it needs to be nicely integrated into the vessel. So design changes are quite limited. And you need to basically build a whole series of vessels with the same dimensions of spheres to make this work. So it's not the most flexible, which is partially why we will talk a little bit more about these membrane tanks in a second. Here, what I just found interesting is mostly the number on the right to see that there is more than 300 LNG vessels in the world order book that are to be built and to be delivered. And that is means there's a continuous increase of voyages and on capacity existing. Doesn't mean that we will increase the 668 ships that you see there by another 300, because of course a lot of them are phasing out. But it is still quite a substantial fleet that we have transporting LNG around the globe. And we saw something about the bunkering stations. And the product, the technology we need on each end. So I'm not going to talk about that, but just a short slide on how do we actually get the LNG into the vessel if we also want to use that as fuel. And if we think of that, then ship-to-ship bunker configurations are found in several ports, and they are under development. It has the challenge that both bodies move, so you need to have these pipes that transfer the LNG with quite some slack, and obviously the boil-off that you have in that area is the most critical. So that poses some challenges there. And what has been developed more and more is the truck-to-ship transfer, and that's most used configuration that we see. It is quick to deploy. You don't need a lot of basic concerns for local authorities that you have to convince if you set up an actual land-based bunkering station. And that may be one of the main reasons why this has been used so far a lot, if you think about using LNG as a fuel as well. But doesn't mean that the other technologies would not work. We saw a little bit about the properties already, and possible hazards are, of course, that you can have a leak as with any other fuel, and you may have an accidental spill. And if that happens, and if you look at the picture on the right, that's a crack in a deck structure of a vessel where there was some spillage. And if you spill cryogenic liquid on steel, then you will most likely result in brittle fracture. And if the ship is floating in water, then there is a bending moment that this is subjected to because of the distribution of buoyancy from the water. So you have some stresses in the deck, and then you create a brittle condition of the material, and that can end up basically with two ships instead of one, in the worst case. And in any case, the local damage may not be nice. So you have to be very careful with that. But it is a standard procedure, so it can be done. And obviously, when there's an accident, there is an accident. You have to mitigate the consequences nicely. Now, when we talk about tanks, then IMO classifies LNG carriers basically with two different types of tanks. They can be independent or integrated tanks. An independent one are the type A, B, and C. They allow a certain amount of pressure, and they need a full secondary barrier or a partial secondary barrier, or maybe none. And the other option is the fully integrated tanks, which is the membrane tank. So while the spherical tank would basically be an independent tank that you just place more or less as cargo in the vessel, the integrated tank needs to be fully integrated into the design, but has the benefit that it can utilize the space that you have on the vessel the best. And essentially, you basically have the hull structure, and you have a secondary insulation. You need a secondary membrane or barrier, and then you have a primary insulation and a primary membrane. And the reason why we are so picky with basically placing the most efficient shape in a hull is what you more or less see here. So if you use a type C tank that is now a little bit cylindrical, you utilize less than half the available space on the ship. If you optimize that a bit, it may go to 60%. But if you try to utilize a membrane type of tank that you embed into the structure so that it can follow that as much as possible, then you can maybe go up to even 90% of space utilization, which is quite nice, and which is why these are dominating what we see out there. So the shortcomings of this a bit are that when you use such a membrane tank, you need a complete double hull vessel. So you need a double hull on the bottom, on the sides, and on the deck. And you need the two membranes. And the second one has to be able to hold the LNG for at least a fortnight. And the two layers of insulation are usually used. And the insulation space is typically inerted with nitrogen. So that would mean you could also use this to stabilize if you would have a leak in the primary barrier, that you could increase the amount of nitrogen to push the LNG back. And you need cofferdams between the tanks, and you need to enter and anchor the containment system inside the hull. And if you have the ship in water, then it will basically bend. And it may bend upwards or downwards, and the ship is not rigid. So it deforms quite a bit. And the tank system that you use has to be able to comply to these deformations, and they are not necessarily small. So you have deformations from the movements of the vessel. And of course, you have possible deformations from the thermal stresses that you expose to the structure in this loading and unloading conditions that you have. And if you look as an example at a GTT Mark III tank here, where we have an insulating panel that is made of reinforced polyurethane foam, that would be the two foam levels in yellow that you see here on the bottom. Reinforced means that there is a layer or multiple layers of chopped fiberglass strands inside of this. They basically act as crack arresters and make that foam stronger. And the density of the foam you can adjust according to the insulation properties that you need. And in direct contact with the LNG, we have 304L stainless steel, 1.2 millimeter thin sheet that has to be specifically made with some kind of corrugations in longitudinal and transverse directions, so that when you have thermal stresses or deformations acting on the structure, that it can cope with them. Because we need to essentially glue and mount this insulation to the inside of our hull structure. And then when the hull structure bends, this needs to be able to bend. And when you cool it down, it wants to contract. And especially the corners may be a problem because it wants to pull away from there. So you see that there is some specific slots in that structure. And if I jump to the next picture, you can see that even better. So that corrugation is placed just above a slot in the primary insulation form. And then there is another slot in that secondary insulation form, so that you have actually a fairly flexible structure. There is some bolts here that may suggest that the whole thing is bolted into the hull structure, but this is mostly temporary while you install it. The actual force is transmitted through these mastic ropes, which is an epoxy resin. And here you get to see a few of the dimensions essentially. So it's a fairly sandwich type of structure with a lot of layers and a lot of glue and a lot of different components, such as wood, halide, and other materials that are acting together to maintain the LNG there. And what I brought you here is just a couple of pictures to show you how such a tank structure may be built up. This is obviously not a realistic, I mean, it's not a full-scale tank, but it's a full-scale insulation system. And we built a mock-up here. And you see, for example, even in our laboratory, this is not entirely straight. So these mastic ropes, they also have the possibility to compensate unevenness of your inner hull, which is supposed to be more straight than for many other ships when you build the LNG hull structure, but nevertheless, you need something like that. You see the mounting bolts, and you can also see that, and it's not a joke here, it's not because it's dirty in the laboratory, but you need to be very meticulous with building this so that there's no dirt and many other things that you would typically not need to deal with in a shipyard environment, because that's usually a little bit more rudimental in a way. So you see every other step requires the vacuum cleaner again. These specific glue components are applied. You see here actually a heating pad, because what is placed here is the secondary barrier. But this is individual modules where that barrier is placed on top, but then you need to bridge the gap between them, and you need to apply that. And on the top, you see this mastic rope, maybe not the nicest consistency here, but nevertheless doing its job to compensate for the differences in tolerances. And then it comes to the internal barrier, so the stainless steel sheet. With this 1.2 millimeters, you can nicely see these corrugations in both directions, so you have a lot of stretching possibilities in both ways. And these are TIG welded without any filler material. So it's actually quite impressive to see that. And you have to do tightness tests or tests for any possible cracks and whether these welds are intact after they are created. You also have to weld above, along these corrugations. And so there's zero tolerance for error. And everything is done by hand. Not entirely. I mean, this was for that small mock-up, it was done by hand. There are some machines that help to do this along the longer seams, but a lot of the small parts may be done manually. Now, if you would like to analyze this, you need to know what material properties you have there. And here is a model of this insulation layup, essentially with finite element methods. It is somewhat simplified, but even so, it looks as coarse as the elements look like this. If you do this on a 3 by 3 meter model, you have a lot of elements there and you have very long run times. So to do this consistently means that you need a lot of computational power if you want to simulate something. Now, what you see here is different material models that may be used for the different material or the different components. Here, for example, you also have to keep in mind it's not just the base material, but because of the corrugation, you need to consider how that structural component behaves, and you need to account for that in the stress-strain behavior. And here you have some mechanical properties for the different plywood components. And this is actually for the polyurethane foam and how this behaves, mainly in compression. Now, when you plug this all together, and you have a test to compare against, which can sometimes be quite nice. You can get to see that, you can get kind of reasonable behavior. You can unfold these corrugations under large deformations. Comparison between experimental force displacement curve and numerical is not ideal, but there's so many things happening that we were quite happy with that. And essentially, the takeaway from this, and especially the test, is that if you would scale this up to a full-scale tank, you would need to penetrate it by almost 8 meters and have about 400 megajoule of energy available before you would cause rupture of the barriers. And that is enough for the majority of the possible collision or damage energies that you have available. So in essence, you can say that such a tank is pretty safe to use, and the technology is quite advanced, but also relatively complex. Now, there is a lot of other tanks out there, of course, one being, for example, the NO96. And that has a lot more wood inside. It's an older generation, but a lot of vessels are out there that may have their shortcomings or benefits that we cannot really talk for time constraints now much about. But one part that is very critical is the corner connection, because you really have the stresses going in those two directions there. You may have a 90-degree corner, which for stresses is never nice. And here you have an interaction between thermal strain and mechanical strain, which makes it extra special. And that is some area you have to meticulously design and try to take care of to compensate all the possible deformations that may occur. And the other parts that are quite interesting in general to look into are obviously not the big surface areas and thermal coefficients or whatnot for this, because you can handle them easily, but the devil is usually in the details. And that could be the liquid dome, the gas dome, the pump tower base support, or a temporary opening that you may need to enter and go in and out while you produce this tank, or while there may be some repairs or other things to take place. And in each of these, you are basically penetrating your insulation layer all the way through the steel structure. So on the dome parts, the liquid dome or the gas dome, you are basically protruding through the insulation layer out through the double hull structure into the outside world. And on the pump tower base, this is where the liquid dome sits on top of. It's a little bit like a cone, and the top of the of this tubing that sits at the end of the liquid dome, where the LNG is filled, sent through to fill the tank, sits on top of that. Which means that if you start to pour the LNG into that, you have a high thermal gradient here between the hull structure that this is somewhat connected to on a much more direct way than in other parts and the inside of the tank. So these parts are, from a thermal situation and stresses that occur, pretty interesting and challenging to look at. Now, to conclude, there is significant amounts of LNG are and will be transported in the next decade still. And the LNG prices seem to continue to be quite low or even decline, which maybe is another contribution for why we will see more transportation and use of that fuel or energy form in the future. And handling of LNG needs specific measures and barriers to be in place. But more or less we can take care of all of them, which is nice. So there's a lot of knowledge on this and experience. There's different containment system technologies, and membrane tanks seem to be very efficient and safe, and also allow for the best space utilization within a vessel. It's fairly advanced, yet it requires meticulous preparation and considerations when you set up and build such a membrane tank. And the details are usually the true challenge. Thank you very much.
Yes, and thank you very, very much for this very nice presentation with the lots of input and a lot of challenges for true engineers. Huh? Yeah, how to find a way to, let's say, deal with these different forces which are ongoing there. So thanks a lot for this. And again, and now let's come to a very short round table discussion with Hans and you. Maybe we can start first with very brief, let's say, update. So if I have interpreted your both presentations the right way, then the message is, and please confirm it or decline it, the message is that if we would like to transport hydrogen in the form of methane, basically the technology is there, the infrastructure is there, the know-how is there. So this is a running system which we simply can jump on. Is this as you see it, or is there any constraints about that? Maybe we can start with Hans and then go to Søren.
I have to say no, because when you really, we are here now looking into the different, to saying that we liquefying, that there are proven projects there to liquefy natural gas up to minus 163 degrees. Of course, there are possibilities to liquefy also hydrocarbon to minus 253 degrees on it that are also available, but with a complete different some processes. You cannot use this type of cascade or something else on it. There you come already to a limit.
Sorry, I said if we transport hydrogen in the form of methane.
In the form of methane.
In the form of methane.
Okay, you mean a derivate? As
it's a derivate,
ammonia.
right. Yeah.
Okay, sorry, then I was on the wrong mood on it.
No, sorry, that's the reason that
No problem. Yes, of course. Then you can transport, once again, this type of ships and even the smaller ones and all the other area. If you're having energy there on it and have LNG transported, there is proven technology the entire chain.
Okay, so thank you very much. And Søren, how do you see it?
Yeah, I would confirm that. I mean, there's always some small adjustments that need to be done and some experiences on these very large scales that we need to obtain. But in general, the hurdle to jump to large scale methane transportation is not that high.
Okay. Then maybe let's come to two of the comments from the chat, and this is to the first presentation. How do the inherent safety analysis for mixed component refrigerant? How to do the inherent safety analysis for a mixed component refrigerant? How do you see this, Hans?
There's always, you see on it how many inventory and what you have in on it. On one side, you try to liquefy a huge amount of natural gas into LNG, which brings you normally the main inventory you are look into with respect to potential leakage. If you go into saying, okay, now you talk about your refrigerant, of course, you have to be the individual look into you are creating more risk on it if you have, for example, in ethylene or propane as well, but they are normally in a small content and in a closed loop. So if you go to your inherent safety and so on, you will look into the hazards or making your hazard or hazard assessment. You will come to the point that the majority of your risk you are creating coming out of your main feed means to produce the LNG and not this and not the inventory. Of course, when you look to the process parts, how you feed, where are your feed to feed, for example, your ethylene loop or your propane loop and so on. All the details is right. They have to be challenged on it. Where you place your propane tank, where you place, where comes your ethylene from, how you feed it, how to put it in. So, but in the end, overall, normally is dominated by your LNG production.
Okay, and the second question is, how can I use the mole and refrigerant mass fraction value for optimization? Can you say something about that?
Yes, but if you start to optimization on it, first you have to choose the right simulation program which can handle all the things on it. And that is one of the core challenge of process engineers are in, even also with the companies we are doing where we have this AB patented, to see on it how you optimize individual pieces in your that starts from your heat exchanger, that starts from your how is your temperature ratio, how is your mole structure, and how you mix your refrigerant. And that is subject to once again, there are a lot of some research still ongoing, and there is not a fixed, say, fit ratio. We're saying what is the best what you can use.
Well, let's say from my point of view as a, let's say, professor here at the university, then I would say this is a doctoral thesis, huh?
Yes,
yeah?
of course.
Okay, so
on it. And if you look on it to your normal, when you have this natural gas curve, there always the challenge is to become as close as possible to this curve on it. And you can imagine with all your small things we need to do, changing some type of an heat exchanger or some surface of a heat exchanger, so some temperature ratio or this on it brings your entire system out of.
Okay, so if anybody is willing from the audience willing to sponsor such a PhD study, so I'm very happy
perfect.
to.
They have to go to you on it, and you have for the next 5 years work enough.
I'm very happy to supervise it. Okay.
Okay.
So let's come to the next point. The question to the second presentation: what is the cost incurred to produce and maintain insulation and vacuum in a LNG transportation truck or tankers? I guess they have no vacuum, right? So
no, they don't. No, it's not needed because it's not so cold. You can do this with the insulation materials like this polyurethane foam and the different layers. Because
maybe sorry on it for the truck loading and for the trucks, the normal trucks if you're transporting say LNG, they are normally vacuum insulated tanks, standard tanks.
Because it's a pressure vessel with a vacuum layer, and you can use that, but you could also do this with a foam insulation. I don't see the reason why not to do this. There would be enough space for it.
Only from my old experience on it, that to having some foam insulation was used in the beginning on it, and not nowadays on it. Also to reducing the board-off rate as well, and having an say inbuilt safety. For example, if something happened due to our normal modern say traffic jams we have and all the other things on it, that you can maintain say longer say period on before you starting to releasing some of the gas to the atmosphere. That's something behind. Also, when you look to river-going ships, which are also coming now.
There is a comment in the chat where they state for small tanks up to roughly 500 cubic meter vacuum insulated tanks are used for LNG.
Correct.
So I mean maybe there are both technologies there. Yeah. So the next point which is coming up: does the cost of storage in the tank affect the cost of gas? If yes, how do we optimize and reduce the cost of storage? So does the cost of storage in the tank affect the cost of the gas? Of course. I mean, when you store it, then I mean the storage has some costs, and therefore you put it on the product. I mean, this is no big deal. And if yes, how do we optimize and reduce the cost of storage? And I think this simple question: how long you store the material and how effective your storage is. Huh?
Yeah, maybe that a little bit more behind on it. One is somewhere beside any safety discussion regarding having full containment storage, for example, on it. Is it normally when we see it when we're starting projects, people saying how many storage you need? Big, nice, as much as possible. When you come to the point to look into on it, if you need 1 tank or 2 tank, you have say some of my slides there was some criteria in to saying we have to start on it. What is your hold up? What is your risk on it if you for your client? How much you need really as throughput? At the end, this comes in how safe is your trade? On how safe is your trade that you need a hold up time of 6 days or 7 days due to bad weather of the gas carrier coming or not coming? On it, can you still serve your client on it, or some having your trade patterns? And this all brings at the end some optimize that at the beginning of a project, most of the projects having 2 big tanks or 2 big storage facilities, because they're saying put everything in, everything big. But at the end, normally that's the start of the end of this process. You can optimize it, means in the size of the individual tanks and the number of tanks, and maybe even of the configuration, what type of tank you can have.
Okay, this is not an optimization problem, you know. So still, if there's anybody out there willing to sponsor a research project, I mean, we are very happy to deal with this. Okay.
Maybe I can make one comment to this. I mean, I think the point was all partially made, but it's this optimization and the cost mostly has to take into account what is the demand. So what do you want to get out of this tank? And it's no point to design one which is so large that it can contain whatever, because you, in the end, want maybe boil off to take place, or because you want something to come out from this. And if you can maintain that balance nicely, that there's always enough delivered, that you have that perfect sweet spot on how much you also take out, then that would be the location you want to attract. So the problem is mostly in scaling this. If you start with a small tank today because you have a low demand and you think that maybe in 10 years it's higher, then you wanted to have a bigger tank already today, but that's not the point. So we need solutions that can cope with this increase in throughput in the years to come.
But normally you have
Okay.
also maybe to add, there's normally a batch operation that you import something, have an intermediate storage and send it out. If you have to increase or send out, you still can put in another intake pump already by having some pump well already right installed right from the beginning. And then you can still increase your throughput on it by just putting in some extra send out pump on it.
Okay,
But
maybe
all part of this optimization process.
Okay. I do understand that, let's say, it depends on the optimization goal and the optimization and the setting of the frame conditions, what you want, how you design the system. Maybe this is a kind of consensus between both of you, but I think you had a different, let's say, optimization goal in mind, and therefore the statements are a little bit different. Nevertheless, we are already approaching, let's say, 8:30, very briefly, and therefore I would like to come slowly to an end. And typically what I do is to make a kind of round table. I mean, or two statements from both of you. I mean, if we look in the next 10 years in advance and assume that the transportation of hydrogen via methane, will gain market importance due to greenhouse gas reduction reasons. What do you think is needed or is necessary to boost this market and allow that we can ship the necessary amount of then green methane around the globe to satisfy the demand? Is there any technological challenges? Are there any market challenges? What do you think is needed to use the existing infrastructure on a more extensive way to transport, let's say, green methane in the years to come to satisfy the customer demands and to satisfy the demand for energy in the maybe Northern Hemisphere, for example? Maybe we can start with you, Hans, and then we move over to Søren. Yeah.
When I see there the future to store, say also for the future, hydrogen via methane in this type of already existing infrastructure, that should be not a problem on it. However, what I see is more a cost challenge on it when you look into the entire chain on it to produce somewhere LNG. And or to have really this hydrogen chain somewhere from the beginning to the end, having seen also that there are still some other options also to have green ammonia and some other ways. I see really a cost challenge of the technology that the overall chain must be per ton produced hydrogen must be lower and lower.
Okay, but you simply see you don't see any technical or other challenges technologically from your point of view, from the liquefaction and regasification units.
If you have really methane and like to liquefy it, there's all in on it. However, you have to see in the normal LNG chain so far already the liquefaction process is more than 25 to 30% of the overall cost of the entire LNG chain. You see, that is already a big part and so on. And at the end, you have to see consumers who pay everything per kilowatt hours.
Okay. Thank you, Hans. Søren.
Yeah, I think that there is not the availability of energy converters on the different scales that we need to cover. They are not available yet.
Yeah.
There are some individual ones there that cover a certain niche, but we don't have the same availability as we have for conventional fuels like diesel that we have right now. So it's a little bit the chicken and egg problem. On the one hand side, they are not developed because the fuel is not there, so there is no market. And on the other hand side, if they are not developed, then there will be no fuel. And there we need a very open communication from both ends to commit and say that this is the demands that we will really have, and we will be open about them. And that's what we have in a pipeline coming, so that we can make that grow at the same time. Otherwise, I really see the problem in the year X, there is a new energy converter out there, and that could be used, but it suddenly creates a demand that is far beyond the capacity. And on the other side, no one builds up that capacity if he or she doesn't know what is required later on. So we need to talk more about this, and we need to be much more open on the demands and the capabilities.
So I understood that you, let's say your statement is that we should, let's say, develop the demand for green fuels in parallel to the provision chains.
Yes.
Because otherwise it will not work out. Yeah?
Yes.
So, but then this is at the end of the day a question of setting the frame conditions.
Yep.
Okay. Anyway, so far so good. I would like to thank both of you again very much for these very interesting presentations, for the discussion what we have had now. So thank you very much for that. And before I terminate this or finalize or close this session tonight, it's already the 6th of our webinar series out of 8. So therefore, I would like to announce that next week, same place, same time, we will have a webinar about production of long-chain hydrocarbon or hydrogen derivatives. So this is basically Fischer-Tropsch crude, for example, or with methanol. So we will have 2 presentations, one about Fischer-Tropsch process from Patrick Leclerc from the German Research Center for Aerospace in Stuttgart. And we will have a presentation about methanol synthesis and methanol to jet processes from Sven Kureti from Technical University in Freiberg. And then after this, on the 28th of February, we will have the last, let's say, edition of our this year webinar about a comparison of hydrogen derivatives and hydrogen supply options. So with this, I would like to, let's say, close this session. Before I do so, I just would like to thank again our speakers of tonight and Wolfram Tuschewitsky, oh, sorry for that, Wolfgang Tuschewitsky, as well as Felix Mendler for making everything working, for taking care that technology works quite nicely. And with this, I wish everybody a beautiful evening. Enjoy yourself. And I would be very happy if I see you again next week, same place, same time, related to production of long-chain hydrogen derivatives. With this, thank you very much and have a beautiful evening. Bye-bye.